Welcome to Lecture 5.2, Properties and Applications of the Laplace Transform. So here are two key properties about the Laplace Transform, two generic properties. I'll tell you a bit about these before we move on. So the first one is that Laplace Transform is linear, and so what do I mean by that? Let me call this property 1 or property I. That means that the Laplace Transform of A times f of t plus b times g of t is A times the Laplace transform of f of t plus b times the Laplace transform of g of t. So anytime you see something as linear, that basically means you can pull apart sums and you can pull out constants. And so integrals behave the same way, and that's actually why the Laplace transform is linear, because it's nothing more than just an integral. But derivatives behave the same way as well. That's why they're called differential operators, and that has to do with why we call linear differential equations linear. I might get into that more in a later lecture. I'm not sure at this point. So the second property, this is more just an observation. You're not really going to use this that much, other than how you normally use integrals. But this is a key, which is why we care about this stuff in the setting of differential equations. So the Laplace transform turns derivatives into multiplication. And so I have to tell you exactly what I mean by that. So I mean that the Laplace transform of a derivative of a function. So let's suppose that you have a function y of t. You compute its Laplace transform, and we usually denote that as capital Y of s. So just with this knowledge, we can compute the Laplace transform of the derivative without actually doing any more math. So all we have to do is we just take our Laplace transform of the original function, multiply by s, and then we have to subtract off this initial value y of 0. So this is a key property that is going to be useful time and time again. And let me actually show you why this is. And the proof of it is just integration by parts. So I'm going to say, so this is the proof of the second property. It's just integration by parts. So let's take the Laplace transform of y prime, and let's use the definition. That is just the integral from 0 to infinity of the derivative y prime of t times e to the minus st dt. That's just the definition of the Laplace transform. So to do this integral, let's use integration by parts. So I'm going to let u be equal to e to the minus st. So du equals minus s e to the minus st. And then dv is going to be y prime of t. Let's say y prime of t dt. And then v is just y of t, the integral of y prime. Okay. So let's use the integration by parts formula. So we get u times v, which is e to the minus st, that's our u, and v is y of t. And we have to evaluate that from 0 to infinity. Then minus v du, or integral 0 to infinity of, infinity, v du. So that's y of t times du, which is, that's this thing. So let's put the negative s out in front. So I'm going to make the negative s, it's going to be positive s, and then put the e to the minus st right here. Okay, so now what do you notice? Well, you might notice that this thing here, what is that? That's the Laplace transform of y. That is just y of s. That's the definition of the Laplace transform. So we can simplify this as, well, before we do that, let's evaluate this. So plugging in infinity into here, we're going to get 0. Now, technically I'm glossing over some details, again, with the limits. And remember in the beginning of last lecture how I said y of t has to be not that big. It has to grow slower than an exponential function, or no faster. That's why, because otherwise, and this is exactly why we need that. Because then when we plug, one of the reasons, because when we plug infinity in here, when we take the limit, this thing's not going to be 0. So this thing here is going to be 0 minus, now let's plug in 0. So we get e to the 0, which is 1 times y of t. Sorry, y of 0. So y of 0. Okay. And then this thing here is plus s times y of s. And when we simplify terms, we get s times y of s minus y of 0. And that's exactly what we claim. That's what we got up here. So I can actually say a little bit more. When I say this turns derivatives into multiplication, we can apply this thing twice. So let's do this down here. So here's a remark. Let's compute the Laplace transform of y double prime. So we could do integration by parts twice, but let's not. Let's just use this formula that we just derived. So the Laplace transform of y prime, think of y prime. Let's write it over here. Y double prime is y prime prime. So let's apply this formula to the derivative of y prime. So in other words, the derivative of the Laplace transform of the derivative of y prime is just s times the Laplace transform of the derivative of y minus the derivative of y at 0. Again, I'm just using this formula, but in place of y, I'm using y prime. Okay, and now what? So let's write this as s times the derivative of y prime, the Laplace transform of y prime, which we have a formula for. It's this thing right here. So let's plug, so let's call this s times y of s minus y of 0. Again, that's all this is. This is just this minus y of 0, y prime of 0. And so now we have a formula. So now this tells us, let's collect terms, and the Laplace transform of y double prime is just this. So that tells us that Laplace transform of y double prime is s squared times the Laplace transform of y. And now we have to subtract off s times y of 0. S times y of 0 minus y prime of 0. So here's our formula for the Laplace transform of the second derivative. And it's not hard to see the pattern. You can come up with similar formulas for the third derivative and the nth derivative in general. Although I think in this class we're not going to use anything more than the second derivative. So I'll just show you this and this one and keep it like that. So the previous slide gave us some shortcut formulas. I said if you know the Laplace transform of a function, f of t, then we know the Laplace transform of a related function, namely its derivative and its second derivative, and so forth. So here's a similar formula. Suppose we know actually I'll show you a couple of them. Here's the first one. Suppose we know the Laplace transform of a function, let's say a function f of t. And then here's a formula for the Laplace transform of that function times an exponential. Just take the regular Laplace transform and shift it to the right by a, where a is the exponent. Here's another formula. Suppose you know the Laplace transform of a function f. Then the Laplace transform of that function times t is just the derivative of the Laplace transform times -1. And in fact, like we did in the previous slide, you can iterate this example and come up with a formula like this. The Laplace transform of that function times t to the n is just the nth derivative of the Laplace transform times -1 to the n. So this is either +1 if n is even, or -1 if n is odd. So let's do some examples of applying these. So let's say example 1, let's call it. Let's say that g of, I'm going to use, so let's say g of t is e to the 2t times cosine of 3t. So recall from, I think it was the previous lecture, or any table of Laplace transforms. So let's use this first formula. So we're going to let this be our f of t. And we know the Laplace transform of that from our table or from the previous lecture. That the Laplace transform of cosine to the 3t is s squared over, oh no, it's not s squared, it's s over s squared plus 9. So what this formula says is, this says, so the Laplace transform of g of this whole thing is this function, but let's plug in s minus 2 in place of s. So the Laplace transform of g is s minus 2 over s minus 2 squared plus 9. Okay, let's do another one. This is example 2, and let's suppose that g of t is t squared times e to the 3t, t squared. So now notice we can use either one of these formulas. We can use this first one. We can let f of t be, so we can let f of, let's use the first one again. Let's let f of t be t squared. So let's call this f of t. So if we do that, then the something to recall also from any Laplace transform table is that and also from the previous lecture, the Laplace transform of t squared is s over, no, sorry, it's not s over, it's 2 over s cubed. And in general, do you remember that the Laplace transform of t to the n, what the formula for that was? It was n factorial over s to the n plus 1. So here we're just using this formula and we're plugging in n equals 2. So 2 factorial is 2, and we get s cubed. So now, this first property says that the Laplace transform of this thing is just this function shifted by 3. So instead of s, plug in s minus 3. So capital G of s is 2 over, instead of s cubed, s minus 3 cubed. And that is our Laplace transform. And notice, we actually could have done this, instead of calling this f and using this first formula, we could have used this last formula for n equals 2 and plugged in and called this f. So let's actually do that. Let me say, or call this f of t and use use property 3 for n equals 2. And what we did here is, for this, we used property 1 for a equals 3. Okay, so to use that, recall from the first lecture or any Laplace transform table that the Laplace transform of e to the 3t equals 1 over s minus 3. Remember that? And in general, the Laplace transform of e to the at was 1 over s minus a. So formula 3 up here says that the Laplace transform of, by formula 3, Laplace transform of this product here is just the second derivative of this guy times -1 squared, which is +1. So this is -1 squared times the second derivative d squared, second derivative of 1 over s minus 3. So what's the second derivative? Let's do this up here. What's the derivative of 1 over s minus 3 is the derivative of s minus 3 and negative first, and that's negative s minus 3 squared, right? Sorry, the negative squared. And then the second derivative is just the derivative of that, so dds of minus s minus 3, negative 2, that's +2 times s minus 3, the negative cubed. And notice that's exactly what this is right here. So this is 2 times s minus 3 to the negative 3, which is 2 over s minus 3 cubed. So sometimes we can actually use multiple formulas to come up with the same answer. So here are, let me box the answers so you can refer back to them. Okay, so thus far in this lecture we've seen a lot of properties of the Laplace transform, and let's now look at an application, which is also in the title of this, Properties and Applications of the Laplace transform. So here's an initial value problem, second order, and let's solve it using Laplace transforms. Now this is something you don't need to use Laplace transforms to solve. We have another method, but let's do this one first, and then we'll start seeing how to do ones where this forcing term is piecewise, and so our calculus methods of the previous section go out the window. Okay, so the first thing to do every single time, let me write this down. First step is apply the Laplace transform. Always the first step. So apply the Laplace transform to what? To this equation. So here's what we do. We say, so the Laplace transform of y double prime minus the Laplace transform of y equals the Laplace transform of e to the 2t. So remember the Laplace transform is linear, so we say if the left-hand side equals the right-hand side, then L of the left-hand side equals L of the right-hand side. Here is L of the left-hand side, and here's L of the right-hand side. So now we use our formula for the Laplace transform of the second derivative to simplify this. So Laplace transform of the second, I'm going to move this over to the left-hand side. Laplace transform of the second derivative is just s squared y minus s times y of 0 minus y prime of 0. So that's Laplace transform of the second derivative. The Laplace transform of just y, that's just plain old capital Y. And then the Laplace transform of the e to the 2t is just 1 over s minus 2. Okay, so let's simplify this. Let's plug in y of 0 and y prime of 0. So y of 0 we're given is 0 and y prime of 0 is 1. So this thing is 0 and this thing is equal to 1. So we simplify this and we get s squared y minus 1 minus y equals 1 over s minus 2. Let's simplify this a little bit. So actually let's talk about what we want to do from here. So first step is always to apply L, and look what we get. So we apply L, we simplify, now we have an equation involving capital Y. It's an algebra equation. You remember from the beginning of the last lecture how I gave an overview as to what we're going to do? Let's summarize it up here. So we have y double prime minus, so we have an ODE, keep wanting to make that negative, e to the 2t, and then we have, it's an initial value problem, so we have y of 0 equals 0, and y of 1, y of 0 equals 1. Let's make that a little better. Y of 0 equals 1. Y of 0 equals 1. Sorry, y prime of 0 equals 1, right? Yeah. Okay, so we have this initial value problem. This is an IVP. And then the first step always is to apply the Laplace transform. So we apply the Laplace transform. And remember what we get? We always get an algebra equation. And this is the algebra equation that we get. I'm not sure if I left myself enough room, but we get s squared minus 1 minus y equals 1 over s minus 2. Okay, so the next thing to do is to solve this algebra equation. So solve. This is, again, like an 8th or 9th grade problem. So let's do that. Let's solve for capital Y. Oh, I didn't mean to draw a line there. Let's solve for capital Y over here. Okay, so how do we do that? Let's factor out. Let's see. So factor out y. We have. So instead of doing that, I'm going to do it down here. We have s squared minus 1 times y equals 1 over s minus 2, and then we have to add this 1, so plus 1. Instead of plus 1, I'm going to write plus s over 2 over s over 2, okay? And now I'm going to simplify this, add these fractions together, and I get s minus 1 over s minus 2. So now we can solve for y. So we get that y equals, let's see, so it's s minus 1 over s minus 2, and then this s squared minus 1, I'm going to factor that. I'm going to factor that as s minus 1 times s plus 1. And now that is going to cancel with that. And so we get that y equals 1 over s minus 2 times s plus 1. So let's update our little diagram. We solve this and we get that y of s equals 1 over s minus 2 times s plus 1. Okay, so now our solution to the original initial value problem, we're almost there, is some function y of t, and it's, well, what function is it? It's some function whose Laplace transform is equal to this guy. So all we have to do now is we have to figure out what function has the property that its Laplace transform is this. And we do that by doing what's called the inverse Laplace transform. Given an algebraic expression, how do we go backwards? So somehow we have to invert this function. And we do that by using our Laplace transform tables. So we look at the table, we say, what function on the table does this remind us the most of? It's sort of like trying to undo an integral from an integral table. Now this doesn't look like anything on the Laplace transform table, but what we do have on the Laplace transform table is the Laplace transform of e to the at is 1 over s minus a. So what we have to do, unfortunately, is we have to write this function as a sum of two fractions. So remember partial fraction decomposition from calculus 2, integral calculus? Yep, unfortunately, that is going to come up again. So we have to write, let's say, break up, write using partial fraction decomposition. Okay, so this is something you've likely forgotten how to do. However, first time you learned it, you were probably memorizing a process, and now you're better at mathematics. So I think you can handle it. This is something that I bet you could rederive. So let's figure out how to do this. It's going to make a lot more sense the second time. 1 over s plus 1 times s minus 2. So we have to somehow write this thing as a over s plus 1 plus b over s minus 2. Okay, so how do we do that? Now we have to rationalize we have to find a common denominator. So we have to multiply s plus 1 times s plus 1 over here. And I didn't leave myself very much room for this, but we have to multiply by s minus 2 and s minus 2 over here. So when we do that, well, now we have to set, so we have to set 1 equal to that. We have to set this fraction equal to that fraction, although the denominators are the same, so we can ignore the denominators and just look at the numerators. In other words, we have to set so we have to set 1 equal to a s minus 2 plus b s plus 1. So how do we do that? Well, this is actually probably going to be easier for you the second time. Let me write it down here. So I'm going to rewrite this down here. So the left-hand side is just 0 s plus 1, and the right-hand side, let's break this up into s's and constants. So how many s's do we have? We have a plus b s's, a plus b s's, and then how many constants do we have? We have negative 2a plus b, so negative 2a plus b. So now, if this is going to be equal to that, then the 0, the coefficient of s on the left-hand side, better be equal to a plus b, which is the coefficient of s on the right-hand side. And the constant term 1 on the left-hand side better be equal to the constant term on the right-hand side. So this gives us a system. Let's write that out. So we get a plus b has to equal 0. Let's make the equal sign a little better. Equals 0. And then the other equation is that, let's write this as negative 2a plus b equals 0. So this is something, I'm not going to do it by hand. I did it ahead of time. Actually, yeah, sure, I'll do it by hand. Let's see. So a equals negative b. A equals negative b. So a and b are opposite signs. And then plugging in, and then eliminating a and plugging in negative b in for a here, we get that 3b equals 1. So we get that b equals 1/3 and a equals negative 1/3. So what have we done? So we have written this fraction into a sum of two fractions. Let me see where I want to move this. Let me do this at the very top. So we have written 1 over s plus 1 times s minus 1, sorry, not s minus 1, s minus 2, as negative 1/3 over s plus 1 plus positive 1/3 over s minus 2. So what does that mean? That means the inverse Laplace transform of this is just the inverse Laplace transform of this plus the inverse Laplace transform of this. In other words, if we want to figure out what function has this Laplace what function of t, f of t, has a Laplace transform equal to this, well, we can say, well, what function has this Laplace transform equal to this plus this? And these are things we can do easily. We get them right away from using the table right here. So remember, the Laplace transform is linear, so we can always pull out these constants. So I'm going to write this as negative 1/3 times the inverse Laplace transform of 1 over s plus 1 plus positive 1/3 times the inverse Laplace transform of 1 over s minus 2. And, oh, actually, I realized I just made a mistake up here, s minus 2. That 2 should be a. Yeah, so that's an a. But, so now we can compute this. This first one is negative 1/3. What function has Laplace transform this? It's just e to the negative t. So e to the negative t. And what function has Laplace transform equal to this? Using our formula, that's e to the 2t. So plus 1/3 e to the 2t. So to summarize, we have found our function. Let's put it down here. I mean, it's right up here, but let's write it down here as well. Negative 1/3 e to the negative t plus positive 1/3 e to the 2t. There's our function. This is our summary of how we solved this differential equation using a Laplace transform. Summarize, we first of all took the Laplace transform of everything and we got an algebraic equation. We solved that, and we got a solution of the algebraic equation, and then we had to manipulate this a little bit. We had to break up the fractions using partial fraction decomposition to get something which is up here in red, and something that we can easily compute the inverse Laplace transform of, and that's what we got. We got a function whose Laplace transform is our solution of the algebraic equation, and that function, that is the solution to the initial value problem. Okay, so on the previous slide, recall that we can compute the inverse Laplace transform of a fraction 1 over s minus a. That is just e to the at. That's just the Laplace transform in reverse. The Laplace transform of this function is equal to this function. And so we also saw a more complicated example. We said if we want to compute the inverse Laplace transform, I think the one we did was 1 over s plus 1 times s minus 2. Then we can write this fraction as, well, we can write this as the inverse Laplace transform of, so we took this fraction and wrote it into sum of two fractions, and that was negative 1/3 s plus 1 plus the inverse Laplace transform of positive 1/3 times s minus 2. And then from here, I think we got negative 1/3 e to the minus t plus positive 1/3 e to the 2t. So next question is, what happens if this thing on the bottom of the fraction doesn't factor? So that's the problem here. So here's a sample problem. Let's compute the inverse Laplace transform of this. So it's not clear what we want. It's not clear how to approach this. So once I show you, I think you'll see how to do it from then on. So recall that the Laplace transform of sine of bt equals b over s squared plus b squared, and we had a formula that, no, let's not do that. Let's do it like this. The Laplace transform of e to the at times a function f of t was the original Laplace transform shifted by a. So these two things together imply that the Laplace transform of e to the at times sine of bt equals b over s minus a squared plus b squared. So when we see something like this, what we want to do is we want to put it in this form and then compute the Laplace transform this way. So if we have it in this form, then we know that the inverse Laplace transform is this thing right there. But it's usually not quite so nice. It's not quite in this form like this, so we have to complete the square. So let's do that. So 1 over s squared plus 4s plus 13. Here's what I like to do. I like to look at this and I say, okay, so we need to write this as s minus something squared plus something else, right? And then we got to figure out what goes there and what goes there. So here's what we have. S squared plus 4s plus 13. It's not hard to see that what has to go here, it has to be positive 2, right? Because we multiply, we don't have any choice with this 4s. Given that this is a 4s, that has to be a 2. Because when we multiply this thing out, this is s squared plus 4s plus 4. So given that, so what goes right here? So if this thing here is s squared plus 4s plus 4, and we have here is 13, then that better be a 9, which fortunately, I set this up this way, is 3 squared. So we're almost there. This looks like something, it looks like that, but it's not quite, because we need, this thing has a b on top, and so we would actually need a 3 on top to have this match that form. So what I always do is I do this. I write down what we need. So we need 3 on top, and then s plus 2 squared plus 3 squared. That's what we need. It's not what we have. So how do we make it what we have? We make it what we have by multiplying by 1/3. So if you multiply by 1/3, now that is precisely, this is in the form that we have here. Okay, so this thing now, compute the inverse Laplace transform. Well, the 1/3 sticks outside, and then this thing on the inside, let's just use our formula. So that came from, let's see, a equals -2 and b equals 3. So this is 1/3 times e to the -2t times sine of 3t. And that right there is our inverse Laplace transform. Okay, so let me do one more. I'm just going to make this one up now. Let's compute so put a line here, compute the inverse Laplace transform of, I'm going to make this one similar. Let's have the same bottom, same denominator, s squared plus 4s plus 13. But on the top, let me put, let's be difficult, let's put, how about 2s? Okay, so now we actually can't quite use this thing here, but we can do something similar. Recall that the Laplace transform of cosine of bt, it's very similar to that of sine. It's s over s squared plus b squared. So the way I keep them straight is sine versus cosine. One of them has a b on top, one of them has an s on top. The one that starts with an s, sine, is not the one that has the s on top. So I never get them confused, but I can see how it's easy to do. Okay, so let's use the cosine formula right here, and let's use that same e to the at times f of t is f of s minus a. And so these things together tell us that the Laplace transform of of e to the at of e to the at times cosine of bt. So this is this thing shifted by a. So now we have to be a little bit careful here. So this is s minus a over s minus a squared plus b squared. It's really easy to forget about this a here, so make sure that you remember that a. Okay, so let's go back to our example. Actually, I'm going to make our example a little bit easier. And I don't want to put a 2 here. It's just going to make it more complicated and I'm running out of room. So let's, is there a way I can, yeah, actually I think I can overwrite that. Okay, so here's going to be our new example. So the first thing to do is we want to put this thing in that form. So well, we've already completed the square. So let's write s over s squared plus 4s plus 13. And so now this is going to be s plus 2 squared plus 3 squared over, and on top, let's make that fraction a little better. So on top we have s. Now that's not what we want. It looks like what we want, but don't forget we need that a right there. So we would need a plus 2. Okay? So here's what I always do. I always write this. So I always write down what we want. Remember that? So here's what we need. S plus 2 squared plus 3 squared on bottom, and then on top we need s minus s plus 2. Remember? S minus a and s minus a to match that. Well, let me actually box that so we can, it's going to be what we need. Okay, but this, so I write down what we want, but that's not what we have. This is what we have. So I need to make it into what we have. So to do that, I'm going to subtract off 2 over s plus 2 squared plus 3 squared. And now this is exactly equal to what we started with up here. Okay, so we know how to compute the inverse Laplace transform of this. Let's actually do that. So the inverse Laplace transform of this is, let's see, this is a equals, same as before, a equals -2, b equals 3. So the inverse Laplace transform is e to the negative a t times cosine of 3t. So this first thing goes to that, but this second thing now we need to figure out what that goes to. So let's do that. So this thing, again, it's not quite what we need. Now this thing we need to put in the form as we have up here. We need to put it in, where was it? This form. So we need that b and this b to be the same. So that needs to be a 3 and not a 2. So remember what I do is I always write down what we need, not what we have. What we need is this plus 3 squared. And now I need to make it into what we have. So how do I do that? Well, let's divide by this 3 to make it a 1. So now these things will cancel. And let's put a 2 out there. Now, do you agree that this is, oh, oops. How do I erase? Okay. Yeah, now do you agree that this whole thing is indeed what we have here? Of course, negative if we include that. Actually, I guess I didn't include that, so maybe well, you can handle it. Okay, so now the inverse Laplace transform of this L inverse, this goes to e to the negative 2t sine of 3t. Oh, and I forgot my 2/3, so times 2/3. And here I'm not including the negative. I'm just going to get rid of that negative, make that plus. Oh, and also over here, I just realized I have e to the negative at. That negative a is, or that should be negative 2, not negative a. So negative, we can make that into a 2. Okay, so now the inverse Laplace transform of this thing. Oh man, again, I keep forgetting that I don't have my laser pointer on me. So the inverse Laplace transform of this is the inverse Laplace transform of this whole thing, which is this minus that. So now we can say that this is equal to e to the negative 2t cosine of 3t minus 2/3 e to the minus 2t sine of 3t. And that is our final answer. So to summarize, when we want to compute the inverse Laplace transform of something where we have a degree 2 polynomial on the bottom, if it does not factor, then we have to use that formula, and we have to use that formula, these two things, and perhaps complete the square and factor out constants and a little bit of algebra, but it's something that you can definitely, with a little bit of practice, you can master this. And I guarantee you this will be on any sort of exam that I give on this topic. Okay, so now I want to compare our old and new methods for solving initial value problems, and I just want to show you the similarity in the structure of the algebra. So let me give you an example, an initial value problem. I'm going to go through here pretty quickly because none of this is really new. So y double prime minus 2y prime minus 3. I'm more interested in pointing out things along the way than showing you how to do this for the first time, because this won't be for the first time. So here's an initial value problem. And so the old method, this is from section 2 or section 3, I guess, is you guess that y of t is e to the rt. You plug this back in and you get r squared minus 2r minus 3 equals 0. Well, so that's r minus 3 times r plus 1 equals 0. So you get right away that y of t equals c1 e to the 3t plus c2 e to the negative t. And let's make that look more like a c. So there is our general solution. If you plug in the initial conditions, then you get that y of 0. So we're plugging in these initial conditions into here. Y of 0 equals c1 plus c2 equals 1, and we get that y prime of 0. And when you take derivatives, the 3 comes out and the negative 1 comes out. So I'm just going to write, I'll say that this is 3c1 minus c2 equals 0. So we have this. So we have a system of equations right here. This is going to reappear. And it's not hard to solve this. This is c1 equals 1/4 and c2 equals 3/4. And so what we get is we get the final solution is y of t equals 1/4 e to the 3t plus 3/4 e to the minus t. Okay, and let me box that. Okay, so that's the old method. Now, the new method, using the Laplace transforms, which you don't need to know to solve this type of ODE. We will need it for later ones when we have discontinuous forcing terms. But the new method is, so we apply the Laplace transform first to everything. 2 times Laplace transform of y prime minus 3 times Laplace transform of y equals the Laplace transform of 0, which is 0. That's the first step we always do. And then we always write these things. So we simplify this. This is y squared, or s squared y minus s times y of 0 minus y prime of 0. This next one is 2. This next one here is 2 times sy minus y of 0, and then minus 3y equals 0. And so based on our initial conditions up here, that is 0. And so we can simplify this as s squared y minus s minus 0 minus 2 times s times y minus 1 minus 3y equals 0. And then so we simplify this and we get s squared minus 2s minus 3. I know I'm doing the algebra a little bit quicker than maybe is comfortable for you, but again, I'm not worried about the algebra. Like, I just want to get through and focus on a few properties of what we get later. So the first thing to notice is that this polynomial is the same thing as this polynomial. See that? And there's a reason for that. This is the characteristic equation, and this also comes up down here as well. Okay, so noting that, moving on, let's write this as y equals, so we can divide, we want to solve for y, so we divide through by this, and we get s minus 2 over s squared minus 2s minus 3. We want to write this using partial fractions, so a over s minus 3 plus b over s plus 1. And now we want to multiply, so we need to multiply s plus 1 over s plus 1 over here. And we need to multiply s minus 3 over s minus 3 over here. And if we do that, then we get a plus b s plus a minus 3b over the denominator, which is s plus 1 times s minus 3, which again, the denominator is the same thing as the characteristic equation up here. So to do that, we need these two things better be equal. So 1s better be a plus b s. So in other words, that means that we have a plus b equals 1. And then the constant term, which is a minus 3b, better be equal to negative 2. So we get a minus 3b has to be equal to negative 2. And this system, notice the similarities between this system and this system. They look very similar, and of course they're going to have the same set of solutions. We're going to get a equals 1/4 and b equals 3/4. That has to be the case. Why is that? Because big Y of s is 1/4 over s minus 3 plus 3/4 over s plus 1. So when we compute the inverse Laplace transform of this, we get our final solution, y of t equals 1/4 e to the minus 3t, that's the inverse Laplace transform of this, plus 3/4 inverse, well, plus 3/4 e to the minus t. Oh, I realized that should be minus t, that should be positive 3t, and this one is going to be minus 3t. So notice that this system and this system has to have the same set of solutions, because that's where these coefficients c1 and c2 come from, and that's where a and b come from, and that's where these coefficients come from. So notice that it's actually easier to do the old method. The Laplace transform is a little bit more work, and that's going to generally be the case, so it's really only used when it's absolutely needed. So to summarize what we did on the last slide, and actually before that, so let's consider an initial value problem, second order, where f of t is the forcing term, and we have our initial, think of this as like position and initial velocity. Then the Laplace transform of, first thing to do is compute the Laplace transform of this, and this is a, and again I'm going to go through this quickly because I'm more worried about where we end up rather than the process. So we compute the Laplace transform of each term, and we get a times s squared times y minus s times y of 0. This is just using our formulas for the second derivative and the first derivative, s times y minus y of 0, and then plus cy. And we can collect terms, and when we collect terms, we get as squared plus bs plus c times y minus x naught times as plus b minus a times v naught equals f of s. So we can, if we solve for s, here's one thing that I want to, here's the big idea here, is that, so not solve for s, we want to solve for y, it's just algebra. We get that y of s equals f of s. This is the Laplace transform of the forcing term. Let me make sure that you can tell that that's capital. F of s over this polynomial as squared plus bs plus c. And then we have as plus b times x naught plus a times v naught over the polynomial as squared plus bs plus c. So what I want you to notice is that this term here, so the denominators are the same, this term here depends solely, if you fix the denominator, solely on capital F of s. That's the forcing term. So this is sometimes this is called the state-free solution. And this thing here, so this only depends on the forcing term, not the initial states, x naught and v naught. So this is the state-free solution, where this term up here depends only on x naught and v naught and not on the forcing term or the input term. So this sometimes is called the input-free solution. So this is like a little introduction to control theory in engineering and how engineers will analyze differential equations. They start with an initial value problem and they say, well, if we take the Laplace transform, we can show that the solution breaks up, or the Laplace transform of the solution breaks up into a state-free solution plus an input-free solution. In other words, that y of s is maybe let's call this ys of s plus yi of s, and where, I'm not going to write it down, I'm just going to say this does not depend, the state-free solution does not depend on the initial conditions, and the input-free solution does not depend on the forcing term. So this is often a starting point for how engineers might analyze solutions to differential equations. From here they may say, well, let's see what happens to the big Y as we change the inputs or as we change the forcing term. And we right now we have a little bit of a grasp as to how that's going to work because we've broken this up into two separate pieces.